Hello everybody, I'm Satya, and today I'm going to talk about an ABI stable architecture for C++ SDK. The name of the architecture is CIB, which stands for Component Interface Binder, and the purpose of this architecture is to bind two C++ components together and also ensure ABI stability. I'm a developer at TomTom, and prior to that I had worked at Adobe for Acrobat, where I had a very pleasant experience because of SDK of Acrobat. So what had happened was that we had a very old plugin of Acrobat that was compiled using Acrobat 5 SDK, and we were able to use that plugin in binary form with Acrobat 10. So 5 version difference, and much had changed in the SDK, and still the binary plugin was compatible with the latest Acrobat of that time. With that wonderful experience, I wondered, would we have expected similar ABI stability had the SDK of Acrobat was based on C++. So I started my personal GitHub project with the aim of finding a solution that can help us create ABI stable library in C++. And today I will be talking about the work that I did during my free time, and I hope I will be able to cover the core of the architecture that I have developed. Of course, I will not be able to talk about everything because C++ is vast and ABI stability is complex. But my aim is to cover the basic architecture that I have created. And for the purpose of this talk, we will confine ourselves to just one aspect of ABI stability, that is the binary compatibility of an older client to work with new library. So the Acrobat story I told you, Acrobat, when it was an executable, for the purpose of SDK, it's a library, and plugin was the client of this library because it was compiled using the SDK exported by the Acrobat. Fine. In this presentation, we will discuss 3 different examples, and in all those examples, we will have a shared library, which is also known as DLL on Windows and SO on Linux-like systems. And we will start with a very simple example where a shared library will export a simple class, and we will see what architectural element we need to put in place to ensure ABI stability. And for this example, we will start with a demo. In the next example, we will see a slightly more complex scenario where instead of a standalone class, we will have a hierarchy of class that will be exported from the library. Then in the third example, we will see a shared library that uses an interface class whose implementation would be provided by the client program. And then we will see what kind of architecture we need to have to ensure ABI stability in that case also. And for this also, we will have a demo. So after all these examples, I will present you a SIB tool that I have created, which can implement this SIB architecture automatically. And then I will give you a report of the case history that I did with a real library. And in the end, we will touch upon things that we could not talk about in the presentation. So the first thing in this presentation now is the demo. So what I have is, in the demo, is a simple library that exports a simple circle class. And in this class, this is a very trivial C++ class. It has constructor destructors, and the name of the class is circle. And it has few non-virtual functions, and it has a virtual function also, and some data members. So it's an example of a very trivial kind of C++ class that you might have seen. And that's it about the library. On the client side, client is an executable that instantiates an object of circle and then makes use of that. And how it makes use of that is it invokes methods on the object of circle and prints the output. So it's a very trivial program, but the point here is we will see how we can ensure ABI stability here. So what I will do is I will run this program and we see this output. So this is what we can expect, right? And since my talk is about ABI stability, I have another set of client library program, but this time this library uses SIB architecture. And I have another program, the same program, simple class, but its name is CBified. So basically this program depends on the library that uses SIB architecture to export its SDK. Okay, so if I run this program, we see exactly the same output, because essentially both the client and the library are actually the same program. It's just that they use slightly different SDK. Fine. Now, imagine in the next version of the library, what happened is that we made some changes in the class. Like like we decided that our circle class should also have information about the center of circle, and such changes can happen, right? So I add two data members to store the center of the circle, and we also decided that our circle class should also have a method to compute perimeter of the circle. So I add another function, perimeter, and I'm purposefully adding this perimeter function before the existing virtual function. So because we know that if we add a new virtual function before an existing one, it will disrupt the virtual table, and it will be, the library will become incompatible with the existing client, right? So fine. So this is the only change we will do in the library, and we will not touch the client. Now what I will do is I will build the libraries. So I use Ninja to build. So Ninja simple class library. So this is the library on which the original program depends on. And as I had said, I have another library that uses CIB architecture. So I have CIB, a simple class library, CIBified. So this is the CIBified library, essentially the same program, but it uses CIB architecture. This is the library on which the CIBified version of the program depends. So I'm just compiling the libraries. The clients remain the same. So now after this, we are in a situation where we have client program that was compiled using the previous SDK of the library, but now the library has changed. Okay, now we'll see how those programs behave. So first I will run the original program. What we see is a different output. It is different than what we had earlier, right? And this is what the ABI instability is. The existing client is no longer compatible with the new library. Fine. What about if we run the CIBified one? So if I run the CIBified one, we see exactly the same output as we had seen earlier. And this is what the ABI stability is. The existing client is still compatible even when the library made the changes in its class, which disrupted its subject layout and which disrupted its virtual table. So I hope it sets the context for the nitty-gritty of the architecture discussion that we will now go into. So the ask here is that we want to export this simple class from the library in a way that we want to ensure ABI stability. So before we go into the nitty-gritty, I would like to mention a talk that was given by Stephanus at CPPCon in 2014. So his idea was that from a C++ library, we can export C-like objects like C functions, opaque pointer, function pointers, those kind of thing. And on the client side, we can rebuild C++ APIs using the C API exported from the library. So that's why he named it hourglass pattern, because the client can use the broad C++, library can also use broad C++. Only in the middle, we have a thin C API. It was a great talk, but it did not cover a few things, like it did not talk about virtual function, interface classes, inheritance. And these are the things we actually use in the C++ library, right? And I had a talk with Stephanus over the email, and he said that his talk was mainly about ABI isolation and not about ABI stability. But nevertheless, I think the core of the architecture of the hourglass interface can be extended to support ABI stability as well. And if you don't know about hourglass pattern, that is perfectly fine. We don't need that in this presentation. What we need is the idea of using an opaque pointer from the different component. We will see that as well in this presentation. So, okay. So what we can do about a C++ class from a library is that instead of exporting C++ class, which we know that can be fragile if we make some changes that I showed in the demo, so we can avoid exporting the class as is. So what we can do is, instead of exporting class, we can export C-style functions. So the original C++ class that we had seen, it had 6 methods, like it had a constructor, it had a copy constructor, it had a destructor, and 2 non-virtual functions, radius, set radius, and it had a virtual function area, right? So corresponding to all those methods of the class, we can create free C-style functions in such a way that the first parameter of all these functions will take a pointer of circle, and the implementation of these functions will just be to delegate to the method of the object that it receives as the first parameter, except the first constructor, which will only return a pointer of circle. It will not take the pointer of the circle class. But other than that, all those methods, corresponding to all the methods of the class, we can have a free style function. And we can export these functions from the library. And on the client side, we can build a class. I will show you how. But I have slightly different idea, and I will explain you why I have slightly different idea. So my proposal is that instead of exporting these functions from library, what we can do is we can export something I call method table. So method table is nothing but a table of function pointers. And here you see I am implementing method table using struct. So struct method table circle, it has six function pointer types, and it has also one member num methods just to keep the track of the number of methods that are present in the table. So this is what we can export. And if you notice, the signature of all these function pointers are exactly same as the function definitions we saw in the previous slide. And one thing also to note here is that instead of circle pointer for all these function signature, I'm using circle impl pointer, which is essentially the same as circle. But it is something to keep in mind. I will tell you why when we go to the client side. So from the library side, what my proposal is that instead of exporting a C++ class or free functions, we should export a method table. So here I am initializing this method table with the pointers to the functions we had seen in the previous slide. And I'm using DLL export. So that is actually the definition of DLL export will depend upon compiler. The point is that we should be exporting just this symbol, the G method table circle, corresponding to the class circle from the library. Now we can go to the client side. So library did not export a class, right? So on the client side, what we can do is we can define a circle class just for the client. So here you see the original circle class definition on the left side, but the circle class definition on the client side, we can have the same name because there is no violation of the ODR principle because library did not export this class at all. On the client side, we can have a circle class with exactly the same behavior, but it will have a data member p-impl, which is a pointer to the circle impl, and circle impl on the client side will just be a forward declared class, and nowhere on the client side there will be any definition of circle impl. So this is the opaque pointer that client will use. And in reality, this p-impl will actually be pointing to an object of the circle class on the library side. We will quickly see what. So we can call this class as a proxy class because it will have exactly the same behavior as the original class, but it will not be the same class, but it will have a p-impl data member that will be pointing to the library side class. Okay, since we have a fresh declaration of class on the client side, we need to have an implementation of this class as well, right? On the client side. But how to have the implementation of this class? If we remember, library had exported the method table. So on the client side, we can import this method table. And if you notice, the declaration of method table on the client side is exactly same as the declaration on the library side because they have to be same, except the circle impl here is just a forward declared class, which on the library side was exactly same as the circle class. Remember? Okay, so the last line you see, DLL import G method table circle will actually import the method table that is exported from the library. And then once we have this method table, we can provide the implementation of all the methods of the circle class on the client side. So for example, the circle constructor that constructs from the radius value, it can call the create function of the method table, and the return value of that, it can store it in its p-impl data member. Similarly, the copy constructor, it can call the copy function in the method table, passing the p-impl data member of the object from which it wants to copy from, and then again initialize its p-impl data member. And rest of the methods like destructor will call the delete function, passing the p-impl, and all the methods can be implemented exactly in the same way. The point to notice is that the first parameter of all this invocation of the function pointer of the method table, they have to be p-impl data member, right? And the rest of the parameters will be exactly the same as the parameters of the method. Okay, now we have a complete class definition on the client side, which uses method table to implement itself. Let's see how it will actually work in real scenario. So suppose the client program instantiates an object of circle and calls a method, for example, an area. What will happen? So the client side constructor of the circle will get invoked, right? And we had seen that it delegates to the function pointer of the method table. And here in this diagram, I'm representing method table as a class, which conceptually it is, right? So we can say that method table is a class with those methods corresponding to all the function pointers it has. And the method table then delegates to the actual method of the class on the library side, right? So for the case of constructor, it was calling new circle, right? And from that, a pointer of circle will be returned. And when that pointer arrives on the client side, that will be accepted as a circle impl pointer, which will be an opaque pointer on the client side. And with that, the client side object of circle will initialize its p impl data member with the pointer it receives. Now the circle object is fully formed, and any method invocation, for example, area, it will go to the implementation of the method on the client side, which then call the function pointer present in the method table, passing the p impl data member as the first parameter, right? Remember? And then it goes to the library side, where it delegates to the method of the object it receives in the first parameter, right? So then the call will eventually happen to the method of the circle class on the library side, which will compute the area and return it, and that value will all the way back come to the client side. So this is how the whole class can be used by the client side, even when library did not export the class. Fine. So how it will actually maintain ABI stability? So if we notice, we did not export in the class from the library, right? So any change in the object layout on the library side or the virtual table layout, that will not affect the client, right? Because it wasn't exported, any change in that will not affect the client. But we did export method table, and any disruption in method table will impact the client. So, but method table is something that is in our hand. We, as an author of the library, can take a full control of method table about how we can modify it in the next version. So what I propose is that no matter where we add the method in the class definition on the library side, all new function pointer entries corresponding to the new method of the class will only go at the end. So the two changes you see in the next version of the method table here, the first change is the number of methods. Earlier it was 6, now it is 7. And the second change is that the function pointer corresponding to the perimeter of the class will go at the end. And we had added perimeter before area, if you remember in the demo, right? And because of that, the existing client that uses method table to implement its proxy classes will keep seeing the function pointers in the method table exactly at the same location where it expects them to be present, right? Because we added things only at the end. Fine, and because of that, we will ensure ABI stability. Now, the thing is, I have introduced method table, and we C++ developers are well aware about virtual table that is generated by the compiler. So a confusion can arise, but there are distinct differences between the two. The method table is basically, it's not a replacement of virtual table. We had seen that the method table was containing function pointers corresponding to all methods of the class, right? Constructor, destructor, virtual function, pure non-virtual function, right? So it's not a replacement. It is only a mechanism for cross-component function call. And it is the method table that is shared between the components. One component exports it and other component consumes it. And that makes virtual table, which is generated by the compiler, remain local. So a virtual table that is created inside a component, that virtual table is only used in that component. Since we did not export the class, we did not export virtual table. And because of that, virtual table remains local. Fine. By now, you might be wondering why we actually needed method table. We could have achieved everything, whatever we have achieved till now, even if we had exported from the library pure C-style functions. Why method table? And that is indeed right. So we could have achieved whatever we saw till now, we could have achieved with pure C functions exported from the library. And on the client side, the proxy class definitions could have used those free functions exported from the library. But use of method table actually makes it very easy to support backward compatibility. So suppose in the next version of the library, when we added a new function to the class, if we on the client side, when we need to define, when we need to implement the new method, since we know that this is not the first version of the library, so it may happen the client that is compiled using this SDK of library might actually be using the old version of library, right? That can happen. We don't know what will happen on the client machine. We shipped our library, but on the client machine, it ended up that it is still using old library, and there is the new client, right? So the method implementation on the client side need to be a little defensive for the new methods. So basically, if it is working with a previous library, the function pointer corresponding to the new method will not be available in the method table, right? So we need to be a bit careful there. We need to check whether the function pointer corresponding to method table is present there or not. And to check that is very trivial. So because in the next version of library, we had seen there were 7 methods in the class. So we can just check number of methods in the method table. If it is not adequate, we can throw a exception. And here I am throwing std bad function call. And the client that compiles itself with the new SDK of the library, that can decide whether it wants to claim backward compatibility or not. If it wants to claim backward compatibility, then it has few choices, like it can decide not to use the new functionality, right? If it will not use new functionality, fine, it will also work with the previous library. But if the client wants to be backward compatible and also want to use the new functions, then it should be ready to accept, to handle the exception bad function call thrown from the client side implementation of the class, right? And with that, it can, after handling this exception, it can mend its ways and manage things nicely. So because of that, I made the design choice to use method table instead of freestyle functions. We have reasons, other reasons also to use method table. We will see in the next example. So, but this was one of the reasons why I made this choice. Fine. The last difference between method table and virtual table is that virtual table inherits. What do I mean by that is that the virtual table corresponding to the derived class also has entries corresponding to the functions that are defined only in the base class, right? But for the method table, since method table is only for cross-component function call, it does not need to participate in the runtime polymorphic call. It does not need to inherit, right? So that is one of the crucial difference. And we will see it in the next example. So that ends the first example. Now we move to the second example, which we have a slightly complicated scenario where we have an inheritance of the classes rather than just a standalone class. So what we have in this example is that we have a base class and we have a derived class deriving from the base class. And I'm using struct in this example because that helps save some space on the slides. And as we know, they are actually same as class. Fine. So base class here in this example contains 2 virtual functions, f and g. And the derived class overrides one of that virtual function of the base class, like g, and it adds another virtual function of its own, that is h. And we want to export these classes from the library, ensuring ABI stability. Again, what I mean by that is that, for example, in the next version of library, if we add new virtual function in the base class, then what will happen is that the virtual table of the derived class will get disrupted, right? Even if we add new virtual function at the end in the base class, right? So basically, this is one of the workaround people use to add virtual function only at the end. That will not disrupt virtual table of that particular class. But if there are derived classes, then the derived class, the virtual table of derived class will get disrupted, right? And that will break the compatibility with existing client. So we want our architecture to handle this case also. And the other thing that can happen in the hierarchy of class is that the derived class in the next version of the library can start deriving from some more parent classes. Such things do happen in real life, right? A class can start implementing one more interface class. That does happen. So we want to know what we can do with the architecture that can ensure ABI stability even in that case. And by the way, this is a choice. If you think that you don't need, your library will not go under such changes, you can decide not to use this part of the architecture, or you can make some tweaking here and there. Fine, but the point is that the architecture I'm talking about does support such kind of resilience in the library as well. Fine. So we no longer export classes in this architecture, right? So we not want to export base class in the derived class. So we will have to export method table. So we'll have to export method table corresponding to the base class in a very similar way as we had seen in the previous example. Just to note one thing is that the free function G, when it delegates to the class method, it will do an exact delegation, like it will use base : G. Because as I said, method table is not for polymorphic call decision. It doesn't want to participate in that. And this function, this free function G will only be called from the method implementation on the client side of the class. So if a decision has been made to call the base class G, we need to make sure that base class G only should be called, even when the P base here, the pointer P base is pointing to the derived class, right? So this is the only thing we need to notice here. So we have the method table corresponding to the base class. Now we go to the derived class. Again, the very similar thing, that we'll have to have free functions corresponding to all the methods of the derived class. But one thing to note here is that we will also need to have a function that can give us a base class pointer given the derived class pointer. I know it's very trivial. We just need to return the pointer that we receive in the parameter. And I will show you why we need it. Please bear with me. We will see that in the next slide. And since we no longer export function, we export method table. So our method table will have an entry for this function as well. Fine. So this is one thing to note here. The other thing to note here is that, as I had said, method table does not inherit. So the method table of the derived class here will only have function pointers corresponding to the methods that are relevant for this particular class, nothing more than that. And we had seen the difference between method table and virtual table, that method table does not inherit. So I'm making that point again. Fine. Now we can go back to the client side and see what we need to have on the client side. So on the client side, again, we will have to have proxy class definitions for all the classes that library had, right? So for the base class, we will have a proxy class base with the same name again. And when I say proxy class, it means this class will have a p-impl data member, which will be pointing to the object of a class on the different component. Here we are on the client side. So the p-impl here in the base class will be pointing an object of the base class on the library side. Fine. So only thing to note here in the base class is that the two things we add to the proxy class, the p-impl data member and the constructor that constructs from the implementation pointer, they will be marked protected because it's a base class. Derived class would like to use them. And then all the implementation of the methods will be just to by just delegating the call to the function pointers in the method table. Fine. Now we can see the definition of the derived class on the client side. Again, things will be very simple. We will have a proxy class definition, which will have a p-impl data member. The one thing to notice here is that the constructor of the derived class that constructs from the implementation pointer will be calling the base class constructor that constructs from the implementation pointer of the base class. And while calling the base class constructor, it will be passing the value that it receives as return value from cast to base. So basically, it will first call cast to base function that will go to the library side because library had the implementation, right? And this function on the library side receives the derived class pointer, which is actually the derived class pointer on the library side because it from client side it is the p-impl data member, which is an object of the derived class on the library side, and that function will return a pointer of the base class of the derived class object, right? And with that, the base class p-impl will get initialized. So what we will achieve is that if we see the object layout of the classes on the client side and the library side, on the client side, the base class part of the derived class will have its own p-impl data member, and the derived class as a whole will also have its p-impl data member. They will get initialized in such a way that they will be pointing to the exact location of their corresponding part on the library side. And suppose in the next version of the library, our derived class start deriving from some more parent classes, so that we don't know how the object layout will be created by the compiler. But since we are calling cast to base function all the time from the client, that function will ensure that the p-impl data member of the base class will keep pointing to the correct location on the of the object on the library side. So that will ensure ABI stability even in that case. Okay, so that ends the second example. Now we move to the third example, which is an interface class, and for that also we have a demo. So I will go back to the code. Fine. So in this example, what we have is we have, just a sec, let me go to the interface class. Okay, in this example, what we have is we have again a circle class, and this time it's a trimmed down version, and this circle class has a draw method which gets a pointer of context. And the context is basically an interface class which has a method draw circle, a pure virtual method. That's why I'm calling it an interface class. And the expectation is that an implementation of this context should have the draw functions implemented. And for example, the draw circle, it should draw a circle. And the implementation of the draw method on the library side, what it does is it calls the draw circle, a method of the context pointer, passing the radius of the circle. So that's it on the library side. And on the client side, which is again an executable, and library, when I say library, I always mean shared library. And on the client side, what we have is client implements this context interface and overrides the pure virtual method of the base class. And it doesn't do anything fancy. It only logs the draw call that it receives. And the client program instantiates an object of draw logger, and it instantiates an object of circle, and then it calls the draw method of the circle, passing the pointer of the logger object it had created. Fine. Okay, so what I will do now is I will run this program. Before that, I will clear the screen to keep things clean. Okay, so the name of the program is interface class. So if I run it, we get this output, and this is what we can expect, right? And as you might have guessed, that we now have another set of the client library program, and this time they are CB-fied. So if I run the CB-fied version, I get exactly the same output, because essentially they are the same program, just that the CB-fied versions use the SIB architecture. Fine. Now imagine that in next version of the library, we make some changes. So for example, we decided that our context interface should also have methods to draw ellipse. That can happen, right? So we added a new pure virtual function in the context class, and again purposefully I'm adding this function before an existing one. Fine. So that's the only change that we will do in the library, and on the client side we will again leave it unchanged, and again we will compile just the libraries. So Ninja interface class library and interface class library CB-fied. Again, this is the library on which the original program depends, and this is the library on which the CB-fied version of the program depends. Fine, I'm building them. Now we are again in the situation that we have the client programs which were compiled using the previous version of the SDK of the library, but now the libraries have changed. And again, I will run those programs. So if I run the original program, I guess you can guess what will happen. It crashes. So because we know that the virtual table that is understood by the library is different than what client understands, right? So because of that, crash is one of the expected behavior. Okay, so what if we run the CB-fied version? When we run CB-fied version, it is exactly the same output as before. So this is what I meant by ABI stability. Even when we made changes in the library side interface, that the virtual table of the interface class, whose implementation is provided by the client, we still ensure ABI stability. So this is what I wanted to demo. And now again, we will go into the nitty-gritty of the architecture, how it is possible. And admittedly, it is going to be a bit more complex than the previous examples that we saw, but I hope I will try my best to explain it. So fine. So what we had is we had a library program, and we had a client program. Library had an interface class and a regular class, and client implemented that interface class, right? If we notice in this example, it is also the library that is making use of a class that is defined on the client side, right? So the draw logger class that was defined by the client, the method of it, the draw circle method, was eventually called by the library, right? So in a way, in this example, it should also be the client that should export its class, right? And how we export class in this architecture? We don't export classes, right? What we do is we export method tables. So on the client side, we need to have a method table corresponding to the implementation class of the context interface on the client side. So we'll have a declaration of method table on the client side. We'll have a free function, again, which will take the first pointer as the context pointer, exactly in the same way that we had seen in the previous examples. And it will delegate to the draw circle method of the context pointer, all on the client side. And we need to wrap this free function into a method table and export it. But we have a little problem on the client side, because it's not the library that compiles using the client, right? It's other way around. The client programs are compiled using the headers of the library, and it links against the library, right? So all the symbols exported by the library is available to the client, but it's not other way around. So here we have a method table defined on the client side. We want that method table to pass on to the library so that library can use it, right? Because we had seen that library was making a function call of the class defined on the client side, right? So we need to pass on this method table to the library. And since we cannot pass it on at compile time or link time, we have to do it at runtime. We will see how. And again, if we go to the library side, since library wants to use a class that is defined on the client side, it has to have a proxy class definition, right? Because in this architecture, we had seen that a component doesn't use a class that is defined by the other component, right? It uses it through a proxy, and the implementation of that proxy is done using method table. We had seen that in the previous examples. So similarly, we will have to have a proxy class definition on the library side, and that proxy class will actually mimic the behavior of the implementation class that is defined on the client side. So here I'm defining a generic context that represents any implementation of interface class on the client side. And since it represents any implementation on the client side, it has to derive from the context interface, right? And as I said, it's a proxy class. What do I mean by proxy class? Is that it has to have a p-impl data member, which will be a pointer of an object class. And again, that the full definition of that implementation class will be in the other component. Here in this example, it will be on the client side. And as I said, library doesn't have the freedom to use the method table that is exported by client, right? It can only have that method table at a runtime. So it will have to have a data member corresponding to the method table as well. And because of that, the constructor of this generic context class will need to get these two pointers as the parameter. And then it will initialize these two members with those pointers that it receives. Once we have the implementation pointer and the method table pointer, we can implement the draw circle method by just delegating to the function pointer present in the method table, right? And again, the first parameter will be p-impl data member, and the next parameters will be exactly same as what the parameters of the method is. Fine. Now, to create this an object of generic context, we need to have an implementation pointer and method table pointer, and they are only available to the client, right? So only client can create them. So basically, client will use this class, right? To use this client by the client from the library, we need to export this class, but we don't export class in this architecture. What we do is we export method tables. So we will have free functions to create an object of this class, and a free function to delete an object of this class, and we need to bundle them up into a method table and export that instead from the library, right? Fine. So that's what we will do for the interface. And if you remember, we had another class also, right? That library was exporting. So we'll have to export a method table corresponding to that class as well. Fine. Now we can go to the client side. So as I said, in this architecture, we don't use any class of the other component directly. We use it through the proxy, and that holds for the interface class as well. So this class, on the client side, we'll have a context class declaration, a proxy class declaration, and since it's a proxy, it will have to have a p-impl data member, which will be a pointer to an implementation class. Fine. But what I say is that on the client side, for the context class, we will also need one more thing, and that will be a default constructor. We did not have this default constructor in the library side class definition, but we need it here, and this architecture actually demands it. As I said, in this example, we don't have the freedom for the library to access all the symbols exported by the client, right? We can only provide the method table to the library side at runtime. And what I propose is that we can use this default constructor as a vehicle to transfer implementation pointer and method table pointer to the library side. So the implementation of this default constructor on the client side, what we can do is we can initialize the p-impl data member by calling the create function on the method table of the generic context, and we will pass this pointer and the pointer of the method table that client had defined, right? And we had seen the definition on the library side. The generic context was getting a pointer of the implementation class and a pointer of the method table, right? So this will actually create an object, generic context object on the library side, and it will return a pointer of the generic context that is defined, that is created on the library side, and that will be received as a pointer of implementation class on the client side, with which the p-impl data member of the context interface will get initialized. Fine. And then we'll have the destructor of the context, which will just call the delete function on the generic context method table, passing the p-impl. Okay. Now we move to the circle class. Again, we'll have a proxy class definition for the circle class as well. It's exactly in the same line that we have seen in the previous example, but I would like to draw your attention to the draw method of the circle class. Nothing unusual, but just want to focus is that the method implementation of draw will call the draw function pointer present in the method table, and the two parameters that it will pass, the first parameter is always p-impl, right? And the second parameter is the same as the parameter of the method, right? But library doesn't understand the context class defined on the client side, right? Because client side classes are different than what are there on the library side. But the p-impl present in the client side class is the one that is an object of the class on the library side, right? So we need to pass the p-impl present in the context class as the second parameter. Fine. Now we are done with the discussion about this architecture. Let's see how it will actually work in the real case. So on the client side, we have, what we do is we create an instance of draw logger. So when we do it, since draw logger is a derived class of context class, the default constructor of context class will get called, right? And what we had done in the implementation of the default constructor of context is that it was calling a create function of the method table of the generic context, right? So basically it was creating an instance of generic context on the library side, passing this pointer and the pointer of the method table, right? And what the value of this will be, this pointer, it will be the pointer of this object we are creating here. So the pointer of the logger itself, right? So this is what we will be passing to the generic context on the library side. And that will create an instance of generic context, and that will be received here and will be stored as the p-impl data member of the context base class, right? Okay. Next, what we do is we call the draw method of the circle class, passing the pointer of the logger. So we had seen in the previous slide, the implementation of the draw method on the client side, it was passing the p-impl of the circle and then the p-impl of the context, remember? And what is that p-impl here in the context? It is the pointer to the generic context. So basically when the draw method of circle is called, the call goes to the library side draw method through the method table, of course. And then the p context that receives here in the library side, it is actually a pointer of generic context. And as we know, the generic context on the library side is actually a proxy class of the implementation done on the client side, right? The proxy class is the one that has the p-impl data member that points to the object of the different component. So the generic context on the library side has a p-impl data member that is actually pointing to the object of draw logger, right? So when library calls draw circle here, the call eventually goes to the method implemented on the client side. And this is how we achieve the library calling client-side method using the method table. And since we had seen that the method table is crucial in ensuring ABI stability, we know that it will be ABI stable, and we had seen the demo. Fine, so we are done with the discussion of the 3 examples. Now I present you my tool that I have developed. So basically the rule of the architecture we talked about are very strict rules, very clear rules, right? So what I propose is that we can have a tool that can read the headers as a library author we would like to publish, and that tool can see that header, parse it, and then create generate the code that implements this SIB architecture. So what I mean by that is that since all the code like definition of method table, initialization of method table, and export it, that is the part of the library side glue code, the extra code. And that this tool can generate, and it can generate the proxy class declaration and the implementation of proxy class that uses method table exported by the library. This tool can generate that also. And this tool can generate method tables separately because it is something that is common between the 2 components. And the other benefit of exporting this method tables separately is that when we change the library in the next version, we can feed this tool the previous definition of method table, so that this tool will understand that it can only add new function pointers in the method table only at the end. And that was crucial for ABI stability, right? And this is what you actually saw in the 2 demo that I gave you. So this tool was actually working behind the scene and ensured ABI stability, which was not possible without this. Fine. So we can have this tool, and I already have this tool, and I have a GitHub page where I have developed it. And finally, how good this architecture is, or is it viable in the real case? So what I did is I did a case study with a real library. So I chose Podofo library, which is an open source PDF library. It's a fairly complex library, but it's not huge, but good enough for my case study. So it exports around 200 of the classes, but it's not a very big library. And what I did is I CIB-fied this library, meaning is that I ran my tool on the headers of this library, which generated the library side glue code and the SDK of this library. And then I compiled all the test programs and example programs which are part of this library. So if you get this library, you will also get test programs and sample programs, example programs. And there are around 30 of them. So I ran all those test programs and example programs and compared the result. And here are the report. So we saw some significant change in the boundary size of the library. So the library was originally around 1.7 MB, but the CIB-fied version of the library was almost 200% bigger than that. And sorry, as you can guess, the additional size of the library will actually depend upon how many methods are there, right? How many methods are there in the library, that the public methods that it wants to export. It doesn't depend on the complexity of the method, because what extra we add are just the free functions which delegates to the methods of the class, right? So they have to be very small inside, small in the generated code part when we create the boundary, right? But since this library wasn't used in itself, so basically the implementation of those methods of class methods were not taking up much size in itself. Because of that, we saw large change in the boundary size, which I think will not be the case if we have a large library, but if we have the similar number of classes. Fine. And we saw some changes in the client side. So this is the size you see here, the cumulative size diff of all the client programs. So these are actually the combined size of all the test programs and example programs. As I said, there are around 30 of them. The size there was, the additional size because of the CIB-fied architecture was that it was 100% more extra size. Again, the same holds true here as well. The programs they were itself were not very complex, and because of that, even the delegation things were significant compared to that. Fine. And the memory usage of the CIB-fied programs was around 5%, less than 5% actually, around 4% extra memory usage. And this is something that we can expect, right? But here again, the extra memory consumption will actually depend upon the number of instances of the class that happens on the client side, right? And it won't be much because the client side classes are actually shallow classes. They don't have much in them. They only have p impl data member that they point to the library side, right? And the performance report is that the cumulative extra time difference of all the programs was less than 0.5%. And I didn't do anything fancy here. What I did is I wrote a script on Linux to run all those programs one after another in quick succession. And I used the time command to measure the complete time of all the programs. And here is the report. And this is again, if you notice, the extra runtime cost will actually be constant all the time because we only do delegation, right? So it won't take much. It will only be constant. So again, depending upon how complex your algorithm is on the client side or the library side, this percentage can go up or down. Fine. So it was the case study report. But what examples we saw are not the only thing that can happen in a C++ library, right? And especially in the modern C++ library, we have many more things. But the good thing is that I already have working examples for almost all of the things that are possible and that are listed here. And you can have a look for all those examples. And I have a GitHub page for that. And yeah, that's it for my talk. Thank you.